Jnanam Paramam Dhyayam. Knowledge is supreme.
Today's module is Noether's normalization lemma and its consequences. This is one of the most fundamental theorem in affine algebras, and we will see it has many consequences. So, today's lecture I will finish the proof of Noether's normalization lemma, which I will abbreviate NL. And today I will prove classical version of normalization lemma. So, the setup is like that. So, K is always a field and A is K algebra of finite type. Last time I told K algebra of finite type simply means that there is a surjective K algebra homomorphism from the polynomial ring in finitely many variables to A. Surjective K algebra homomorphism, surjective. So, this means that this A is generated by the K algebra generated by the images of capital X's. So, those I will denote by small x's. Okay, so the normalization lemma says that this is a classical version. And then next time we will see more general than this. So, with the same notation, there exist elements Z1 to Zm in A such that 1 Z1 to Zm are algebraically independent over K. This simply means if you take the map from the polynomial algebra in m variables to the subalgebra generated by Zi's, this is the notation for this is the subalgebra of K subalgebra of A generated by Z1 to Zm. That simply means this is the smallest subalgebra of A which contains Z1 to Zm, and this map is the evaluation map Ez epsilon z, which is capital Zi goes to small zi. Algebraically independent means this map is an isomorphism, K algebra automorphism. So, that is one. And second says A is integral over K Z1 to Zn. Integral means every element of A satisfies the monic equation over this subalgebra. Moreover, if x1 to xn are algebraically dependent, dependent over k, then this m is strictly less than n. So, this is what we will prove today. To prove this, I will need one key lemma which has also independent interest. So, let me prove the lemma. We will prove this after we finish the proof of the lemma. So, the lemma we need is K is a field, and suppose I have a non-constant polynomial f in several variables k x1 to xn, non-constant. Then there exists a K algebra automorphism of the polynomial algebra k x1 to xn to itself K algebra automorphism such that it fixes the last variable. Let us give it give the name for this. This is phi. Phi of xn is xn, and this given polynomial f becomes monic in xn. F looks like a some constant times xn power d plus f d minus 1 xn d minus 1 plus f1 x plus f0, where this fj's, where this a is a non-zero constant. I will use this notation for non-zero elements of the field k cross, and these fj's are polynomials in y1 to yn minus 1, where this yi is, this is for any j is from 0 to d minus 1, and yi's are nothing but images of capital X's under phi. This is for I equal to 1 to n minus 1. So, it is very simple that given any non-constant polynomial in several variables, we can make it monic in one of the variables by changing the variables. And when one say change of variable, that simply means under automorphism. Sorry? No, but f is here, no? See the same f here. Okay, so after proving the lemma, we will see something more about the automorphisms and this one. So let us prove the lemma first. So proof of the lemma is very simple. Let us see. So I claim that there exist natural number of positive integers gamma 1 to gamma n minus 1 such that, see, I want to give automorphism. So I just have to give values on xi's such that they are surjective, such that yi, which is phi of xi, this I want to define it as xi minus xn power gamma I, and I is from 1 to n, 1 to n minus 1. So, if I define phi like this, phi of xi is this, and of course, xn we want it fixed. First, observe that this phi is an automorphism. That is simple, because once you only have to prove it is surjective, because surjective K-algebra homomorphism will also be injective, because both these are Noetherian rings, and surjective homomorphism from a Noetherian ring to itself is always injective. That you must have seen in the first course of algebra. So, if you have not seen, please check that. So, it is clear that xn is in the image, and once xn is in the image, each xi is in the image. Therefore, it is clearly automorphism. So, phi is clearly K-algebra automorphism. Of K x1 to xn. And now we just have to check that if I plug it in this f, if I plug this yi's xi equal to, I will write xi equal to yi plus this and just plug it in f, and we will check that then f becomes monic in xn. So, let us do it quickly. So, that is very easy. So, f is a polynomial. So, f is a finite sum of monomials. So, f is therefore summation is running over finite monomials. So, a alpha x alpha, and alpha are finitely many indices, right. So, alpha is in this, where this is a finite subset of n power n. This is a finite subset, and these a alphas are elements in K cross, and we standard notation we use x alpha means x1 alpha, x1 power alpha 1, etc., xn power alpha n. That is the standard calculus notation. Okay. So, now we want to put xi equal to yi plus xn power gamma I for I equal to 1 to n minus 1. So, this will become, this f will become summation alpha in this capital alpha, a alpha, and that x1 power alpha 1, xn power alpha n. So, this will become summation alpha in this a alpha, x1 I will put y1 plus this. So, y1 plus xn power gamma 1 power alpha 1, etc., last but one term is yn minus 1 plus xn gamma power n minus gamma n minus 1 power alpha n minus 1, and the last here is xn power alpha n. This is what, just plug it in till you. Now, so when you expand by binomial, what will you get the coefficient here? So, when let us put degree, gamma degree of a monomial x power alpha, this is the weighted degree, where you give weights to x1, gamma 1 and xn minus 1, gamma n minus 1, and last one is 1, xn as weight 1. So, this is gamma 1 alpha 1 plus gamma n minus 1 alpha n minus 1 plus alpha n. This is the weighted degree. So, if you do that, if you expand it, so I want to choose, see we want to show that there exists gamma 1 to gamma n minus 1. So, I want to choose, so choose gamma 1 to gamma n minus 1. Let us, I want to give this, abbreviate this, this is, let us call it omega alpha. So, for each alpha in capital this, we put omega alpha equal to this expression if you like, that is called the gamma degree of the monomial x alpha. And we choose gamma 1 to gamma n minus 1 such that all these omega alphas are different. For all alpha beta which appear in this polynomial and different alpha. So, this is what we have to justify. So, this is possible because what we do is, for example, take gamma I to be g power I, where g is bigger than all the components of all the alphas which are appearing here. So, this where g is bigger than supremum of, this is a finite alpha j, such that alpha which is alpha 1 to alpha n which is in alpha and all j. So, in this capital gamma only finitely many tuples appear and there are finitely many components, and I choose a natural number which is bigger than everybody. So, now this, if you look at this expression, this will be a g-adic expansion. So, when I take gamma equal to g power I, that omega alpha looks like, I will write this term first, alpha n plus alpha 1 g plus alpha n minus 1 g power n minus 1. So, these alphas are much smaller compared to g. So, they are nothing but the g-adic g digits. So, alpha n, alpha 1, alpha n minus 1, they are g digits of omega alpha. So, when if omega alpha equal to omega beta, then their digits will be equal, but then alpha will be equal to beta, right. So, we can always choose because there are finitely many components. So, therefore, in this expression only one maximum will come, because all the monomials have different degrees, this is gamma degree. Therefore, only one is finite set and all elements are different. So, when you compare, only one will be maximum. So, that means there exists unique alpha which is alpha 1 to alpha n in this with d equal to omega alpha is maximum, where gamma varies in, no, alpha varies in this capital alpha. So, therefore, when I plug it in, you write f will look like that coefficient of that maximum a alpha, and then x n power omega alpha plus now the lower degree terms. So, that will be summation j is strictly less than omega alpha and some coefficients that I will call it Fj's and xn power d minus j, where Fj's are now, you see, if you see this expression, when you expand it you will get y's, and those Fj's are the polynomials in y's. J is from 0 to d minus 1. So, that is what we wanted to prove. It became monic in Xn with coefficients have changed, but again those y's are again polynomials in Xx. So, that proves the lemma. G, this one, no, all alpha j's, all the components of alpha where alpha is varying in that finite set. No, G is a fixed bigger, very big natural number. Oh, here, yeah. Thank you. Okay, so that proves the lemma. Now let us come back to the proof of the normalization lemma, classical. So, proof of NNN. So, what do we want? We want to find elements Z1 to Zm such that they are algebraically independent and A is integral over the subalgebra generated by Z1 to Zm. So, this I am going to do it by proof by induction on N. Remember, N is the number of algebraic generators for the finite type algebra A. So, if x1 to xn are algebraically independent, over K, then we have nothing to prove, because I will take m equal to n and Z1 to Zm as x1 to xn. They are algebraically independent, and then A is integral over A, that is obvious. So, if x1 to xn are algebraically independent over K, then the assertion is trivial. Simply take m equal to n and zi equal to xi. So, we may assume they are not algebraically independent, that means they are algebraically dependent. So, we may assume x1 to xn are algebraically dependent over K. That means there is a non-zero polynomial in n variables. So, when I plug it in the variables equal to these elements, when I substitute, then it becomes a zero polynomial. So, that is, there exists non-zero polynomial f in n variables x1 to xn such that f of small x1 to xn, this is 0. Okay, so I have this non-zero polynomial and non-constant actually. Obviously, it has to be non-constant. so non-constant. So, this polynomial I will make by using lemma, I will, by using the automorphism, I will change it, I will make it monic in one of the variable, monic in the last variable. So, that means by lemma we may assume that f looks like some non-zero constant x n power d plus f d minus 1 x n power d minus 1 plus f 1 x n plus f 0, where these f j's are polynomials in y's, y 1 to y n minus 1, j is from 0 to d minus 1, and yj's are the changes or images of that those x's. So, when I plug it in now small xi, this becomes 0. So, I multiply by A inverse of f of, this is a non-zero constant, x1 to xn, this is 0 because f of x1 to xn is 0. On the other hand, when I plug it in, what do I get? This A inverse I cancelled it, so it becomes monic in xn, small xn. So, small xn power d plus now this these capital Y's, they are polynomials in x's. So, I can substitute in this small x's. These I will call it yj's. They are the elements in A. So, we will get here f d minus 1 small y 1 to y n minus 1 x n power d minus 1 and so on, f naught small y 1 to y n minus, clear. So, these coefficients are in the subalgebra generated by y 1 small y 1 to y n. F j's evaluated at small y 1 to y n minus 1, they are actually elements here. So, and this satisfy monic x n satisfy monic equation over that. So, this simply means x n small x n is integral over k y 1 to y n minus 1, this is. So, we have A here and A is generated by small x 1 to x n, this is x 1 to x n, which was k y 1 to y n minus 1 and x n, and x n is integral. So, this contains k y 1 to y n minus 1 and this x n is integral over this. So, therefore, this extension is integral because it has only one extra element and that is integral. So, this is the integral extension. Now, you see I am going to apply induction to this induction hypothesis to this new algebra, which is finite type and generated by n minus 1 elements as an algebra. So, by induction hypothesis, there exist elements z 1 to z m in this k y 1 to y n minus 1 such that, see what was our requirement, I just want to show you NNL. such that they are algebraically independent, Z1 to Zm are algebraically independent over K, and K y1 to yn minus 1, this is integral over K Z1 to Zm. This is the inductive hypothesis. So, we have checked that this A is integral over this and this is integral over this. So, by transitivity of the integral extensions, A is integral over, see, A is integral over K y1 to yn minus 1 and this is integral over K Z1 to Zm. This is integral and this is also integral. So, this one is integral. So, that is what the second requirement. And just one thing, that by induction this m is less equal to n minus 1, so which is less than, strictly less than n. So, it proves the moreover part also. You see, moreover part is, I will just bring it here, moreover part is, if x1 to xn are algebraically dependent, then that m is strictly smaller than n. So, that comes here.